Hello, my name is Charles deBoisblanc, and today we'll be discussing cochlear implants. We'll begin by reviewing the anatomy of the ear, and then we'll go over audition itself. Next, we'll review auditory pathologies. Then we'll go over senescence and its effects on audition. And finally, we'll discuss cochlear implants. The anatomy of the ear is divided into three portions: the external ear, the middle ear, and the inner ear. The pinna, also referred to as the auricle, is a cartilaginous structure that functions in funneling sound into the ear canal. The whorls and recesses of the pinna are what direct the sound into the ear canal. The ear canal, also called the external acoustic meatus, is an S-shaped tube in which sound travels from the external ear to the middle ear. Cartilage makes up the exterior portion, and bone makes up the internal portion. The ear canal is lined with sebaceous glands that release sebum. Sebum mixes with dead skin cells to make cerumen, or earwax. Cerumen moves externally and falls out of the ear. It functions in preventing foreign particles from entering farther into the ear. However, it can prevent proper hearing if it becomes impacted. The tympanic membrane is a concave membrane that vibrates when it receives sound. It conducts the auditory stimuli to the auditory ossicles. Pressure on both sides of the membrane must be equal to allow the membrane to move freely. If the pressure on either side of the membrane is too high, membrane motion is restricted and stimuli potency is reduced. Mastoid air cells function in the middle ear to release air to adjust for any changes in pressure. The malleus, the incus, and the stapes comprise the auditory ossicles. The malleus is the bone attached to the internal side of the tympanic membrane in the incus. The incus is a bone connecting the malleus and the stapes, and the stapes is a bone connected to the incus and to the oval window. The oval window receives auditory stimuli conducted from the ossicles and produces waves inside the fluid of the inner ear. The inner ear contains both the vestibular system and the cochlea. The cochlea is called the organ of hearing and contains the organ of Corti. The vestibular system is constituted by semicircular canals and otoliths. This system is critical in maintaining balance. Specialized hair cells called macula within the vestibule contain small cilia that can sense vibrations. When the head moves, the membrane of the chamber shifts, activating the macula and sending signals to the brain to allow for balance. Small granules within the membrane of the chamber called otoliths weigh the membrane down. These otoliths could cause problems if they become loose. If an otolith escapes the membrane, benign paroxysmal positional vertigo can occur. Crystals will move even when the cochlear fluid is still, causing dizziness. This is treated by getting the crystal back into the right spot through canalith repositioning maneuvers. The organ of Corti is one of the most critical portions of the ear. It is supported by the basilar membrane and has hair cells. These hair cells have stereocilia that function to expand the surface area for stimulus detection. The tectoral membrane converts mechanical signals received from the middle ear to electrical signals, and these signals travel to the brain. The organ of Corti enables us to tell loud and soft sounds apart as well. One of the most important parts of the organ of Corti are the hair cells themselves. Hair cells function in detecting sound and converting it into an electrical signal. Hair cells that make up the organ of Corti are the inner and outer rows, which are divided by the tunnel of Corti. Hair cells must be inundated in endolymph, a fluid that contains a high concentration of ionized potassium. The potassium creates an electrochemical gradient inside the cell, and these gradients allow the signal to occur. When the cochlear wall is disturbed, it moves, causing the tunnel of Corti to rock and displace the hair cells. Hair cells function in different capacities depending on their location. Outer hair cells function as cochlear amplifiers, increasing frequency and amplitude selectivity. Inner hair cells, on the other hand, relay signals from the environment to the brain. Hair cells don't use normal synapses. Instead, they use mechanical gates. At rest, mechanically gated potassium channels are partially open. Partial depolarization will open calcium channels, causing neurotransmitter release from the hair cell. Stereocilia are mechanically bent to allow potassium channels to open, causing depolarization of the cell. This causes action potentials to fire more rapidly. Now that we've reviewed the anatomy and physiology of hearing, we will be reviewing different types of hearing loss. Conductive deafness is the inability to hear because sound waves are physically blocked from moving inner ear fluid. This can be caused by multiple things, including cerumen impaction, ruptured eardrum, ossicle restriction from movement, and fluid accumulation from otitis media. Sensorineural hearing loss is hearing loss occurring from cochlear damage or damage to the nerves connecting the inner ear to the brain. People with sensorineural hearing loss may have a difficult time hearing faint sounds. Speaking louder may help these people hear, but the speech may not be clear. Finally, neuroprobicusis, hearing loss due to aging, is a progressive process that often affects hearing bilaterally. Exposure to everyday noises can damage cochlear hair cells with time. The destruction of the cochlear hair cells is what causes hearing loss. In fact, by age 65, the average person loses over 40% of their cochlear hairs. The hair cells that are most frequently lost are the ones that detect higher frequencies. People suffering with neuroprobicusis typically complain of slurred speech, difficulty understanding conversations when others are speaking in the background, difficulty distinguishing high-pitched sounds, and either unilateral or bilateral tinnitus. Women's voices are often more difficult to understand than men's. To diagnose neuroprobicusis, physicians use otoscopes to check the outer ear to look for damage to the tympanic membrane, inflammation, infection, or any blockage. If probicusis is suspected, patients can receive audiograms from audiologists. In an audiogram, patients raise their hands when they hear sounds. If patients are unable to hear certain tones, the patient may have hearing loss. There are multiple different treatments for probicusis, including hearing aids, bone-anchored hearing systems, assistive listening devices, hearing pills, and cochlear implants. Hearing aids are instruments that amplify sound that can be worn behind or in the ear. Bone-anchored hearing systems are surgically implanted devices that convert sounds to vibrations and relay that to the inner ear through the skull. Assistive listening devices are applications on phones or other devices that can amplify sound. Hearing pills are drugs that are in clinical trial that can treat tinnitus and deafness, and cochlear implants are surgically implanted devices that are used in patients who are considered profoundly deaf. Cochlear implants are surgically implanted devices. They're bipartite, with one external portion placed behind the ear and one internal portion placed under the skin. This system removes the cochlea from the equation, and it converts sound into an electrical signal so that these signals can be relayed to the auditory nerve. These don't grant people full hearing capabilities, but they do grant people the ability to recognize sounds. The external portion of the cochlear implant has multiple parts. A microphone detects sounds from the environment. A speech processor will take these sounds and distinguish them, and a transmitter will transmit these processed sounds to a receiver inside the body. The internal portion of the cochlear implant has a receiver and an electrode array. The receiver converts the processed signal into electrical stimuli, and the electrode array receives these electrical stimuli and applies them to the auditory nerve. There are some limitations to cochlear implants. There's a difference in the quality of hearing between normal hearing and restored hearing from these implants. Frequency resolution is reduced, as electrical signals are limited in the ability to distinguish between frequency differences, and the electrical signal is limited in how strong it can be. Ideal candidates for cochlear implants are younger than 2, as they will not be developmentally disadvantaged. However, there is no age limit for cochlear implants. Cochlear implants are effective solutions for treating deafness, but what if we could just regrow dead hair cells? A recent paper entitled "Notch Inhibition Induces Cochlear Hair Cell Regeneration and Recovery of Hearing After Acoustic Trauma" does just that. Before diving into this paper, I'd like to do a cursory review of the notch signaling system. When hair cells are made, notch signaling guides the cell's differentiation. Notch signaling is a critical pathway that maintains homeostasis in adults. This signaling modulates juxtacrine cellular signaling, which is an important system of regulation for multiple tissue types. Notch receptors are membrane proteins with a transmembrane domain, an extracellular domain, and an internal domain. Notch receptors release the intracellular domain after contacting gamma secretase, and the intracellular domain will lead to transcription factor production. Notch will normally target MYC, P21, and HES family genes. Researchers manipulated Notch signaling to make new hair cells in hearing-impaired animals. They wanted to investigate whether damaged cochleas contained cells that would be used as precursors, and they focused on gamma secretase inhibitors to do just that. Multiple methods were used in this paper. Firstly, cochleas and utricles of neonate transgenic mice were degraded by proteases and cultured on petri dishes to make inner ear spheres. Gamma secretase inhibitor was then added after the cells attached to solid media. Mice that were deafened in an acoustic chamber had gamma secretase inhibitor injected near the round window. The inhibitor was also given orally, and hearing was measured before and after administration of the inhibitor using auditory brainstem responses. Immunohistochemistry for tissue from the organ of Corti was performed as well, and cell counts done in this tissue were then recorded. In Part A of Figure 1, the researchers found the most potent gamma secretase inhibitor to be LY411575. I'll refer to LY411575 as just gamma secretase inhibitor through the rest of the presentation for simplicity's sake. Part B of Figure 1 confirmed the gamma secretase inhibitor's efficacy. It saw an increase in myosin 7, which indicates hair cell growth in gamma secretase inhibitor-treated inner ear spheres. Part C of Figure 1 is a visualization of hair cell growth with the gamma secretase inhibitor. Part D shows that it works on both outer hair cells and inner hair cells. In Part A of Figure 2, we see a whole mount organ of Corti stained for myosin 7A. In Part B of Figure 2, we see one row of inner hair cells above 3 rows of outer hair cells in the top panel. The middle panel of Part B is showing staining for supporting cells found in the organ of Corti. The final panel shows the prior two panels overlaid. In Part C of Figure 2, hair cell-specific caspase activation was used to destroy hair cells. In the presence of the gamma secretase inhibitor, there's decreased expression of SOX2 and increased expression of myosin 7A. SOX2 is a gene that is important for suppressing neural differentiation and modulates the renewal of stem cells. In Part D of Figure 2, the organ of Corti specimen that had been damaged by caspases was able to be treated with the gamma secretase inhibitor. Specimens that were treated with the inhibitor exhibited more myosin 7A positive cells and fewer SOX2 positive cells. This likely means that SOX2 positive cells differentiated into hair cells after the inhibition of Notch signaling. In Figure 3, gene expression of noise-exposed mice was evaluated. In Part A of Figure 3, injections of the gamma secretase inhibitor into the ear decreased expression of HES5 after exposure to noise when compared to mice not given the inhibitor. HES5 is a gene activated by the Notch pathway that represses ATOH1. ATOH1 is a gene that is involved in neural differentiation. In Part B of Figure 3, injections of the gamma secretase inhibitor into the ear increased the expression of the ATOH1 gene when compared to wild-type mice. Together, this figure shows us that activation of Notch signaling through hearing damage is possible. To gather data for Figure 4, researchers used a Cree reporter strain or lineage tag to trace SOX2 positive cells inside the organ of Corti after applying the ototoxic drug tamoxifen. They also relied on a double deafening technique in which mice that had been given tamoxifen were deafened in an acoustic chamber and then either given a vehicle or the gamma secretase inhibitor. These methods are important because, to quote the paper, cells expressing SOX2 at the time of tamoxifen administration became positive for green fluorescent protein and retain expression even if they lose the SOX2 expression. In Figure 4, we see many cells positive for myosin 7A were also positive for green fluorescent protein. This indicates transdifferentiation from SOX2 positive cells, to quote the paper. The cells labeled with green fluorescent protein were found to express Prestin, an outer hair cell marker. They did not express the inner hair cell marker CTBP2. This means that preventing notch signaling by using the gamma secretase inhibitor allows for supporting cells to transdifferentiate into hair cells in certain portions of the cochlea. In Figure 5, we see outer hair cells proliferated in the central portion of the cochlea when treated with the gamma secretase inhibitor. This is evident in the increased number of hair cells in Figure 5a and the decreased number of supporting cells in Figure 5b. Together, these data indicate that supporting cells can differentiate into hair cells, that notch signaling can be activated by hearing damage, that gamma secretase inhibitor LY411575 inhibits the notch pathway to promote neural differentiation and growth, and that treatment with gamma secretase inhibitor allows for the regrowth of outer hair cells in mice. To conclude this presentation, hair cells are critical for audition. Neural pubicusis can cause the loss of hair cells, but there are multiple methods to treat pubicusis. Cochlear implants allow the conversion of auditory stimuli into electronic impulses that can be applied to nerves, allowing the deaf to hear. This is our current means to treat neural pubicusis. However, hair cell regeneration is a promising way to treat deafness in the future.